So this is week 2 of the problem solving session for applied thermodynamics course. So previous week we started with entropy balance for a control volume. So this week is also a continuation of that. We will see some more problems doing an entropy balance, and let's get started. So the first problem for today is we have a rigid vessel which initially contains 1 kg of saturated R134A vapor and 15 kg of saturated R134A liquid at 900 kilopascal. A relief valve is provided on the top of the vessel in order to maintain the pressure inside the vessel constant at 900 kilopascal by allowing saturated vapor to escape. So heat is now added to the vessel until all the liquid evaporates. Determine A, the mass of vapor that escapes, and B, the heat supplied. C, also determine the entropy generated during the transient process. And the assumption that what is made is, assume that the heat is supplied from a reservoir at 50 degrees Celsius. So that's the question. So what you basically have is a cylinder, just like your normal LPG cylinder, liquefied petroleum gas. So where there is a combination of butane and propane. Just like that, you have a liquid petroleum gas there. When you're burning it, the liquid evaporates, so and the vapor is coming out, and that is getting burnt. So just like that, you are having a valve, you are opening that valve and letting the gas coming out, and in this cases you are burning it, but our case we are leaving it out. So the idea both are same here. So what happens is this gas, until the last drop of liquid is present, what you have inside the cylinder is your vapor pressure of that molecule or whatever fluid is there. So the vapor pressure of the fluid is what is there inside the cylinder at any temperature. So here we are adding heat. So why are we adding heat here? So what happens is you are letting gas out through the valve. So this is like an expansion process. So what is happening is your gas is expanding. So in or you can say that if you put a control volume, some mass is escaping out, so your internal energy is coming down. So basically what happens is your temperature should go down. So so that's what other point of view is there's an expansion and your temperature will drop, so does your vapor pressure corresponding to that temperature. So to maintain this at this 900 kilopascal, since the temperature is dropping, you need to keep it at the same constant temperature. You heat it, and that is done using a reservoir which is at 50 degrees Celsius. So that is the idea of the question. So now I guess the question, what it describes and why it's been done, is clear. So we have a 134A gas cylinder which is initially contains a 1 kg vapor and 15 kg liquid. So we know the total mass of the gas present and at what pressure, and what we need to determine is so we need to find out when this whole 15 kg of mass of liquid is evaporated. So how much gas is left. So it's not, you can say 15 kg, but all there is no liquid present. So at that case, what is your mass present inside the cylinder, or mass which has escaped, and how much heat has to be supplied to let all the liquid evaporate and leave. And also for this process we need to find out a entropy generated. So we'll see how to solve this. So first is what we know is that we'll calculate the dryness fraction. So initially we know there is 1 kg of vapor and the total kg is 16 kgs. So 1 by 16 will give 0.0625, and from chart we can find out that the specific volume of liquid and specific volume of gas for 900 kilopascal are 0.858 into 10 power minus 3 and 0.0227 meter cube per kgs respectively. And similarly we are finding out the internal energies, and from this we can calculate what is my specific volume at that given point for this mixture. So the specific volume is given as the specific volume of saturated liquid plus dryness fraction into my difference in specific volume with saturated vapor and liquid. So doing that we will get my specific volume is 2.223 into 10 power minus 3 meter cube per kg. And similarly my internal energy at state 1 where the valve is not opened. So this is the state 1. So at that point my internal energy is 110.1 kilojoule per kg. So now the volume of the vessel at this state 1 is, we know the initial mass present and we know the specific volume. So specific volume times mass will give me the volume occupied or the volume of the cylinder. So that is equal to 0.0356 meter cube. So that is my volume of the cylinder. So now since saturated vapor fills the entire vessel at the final state and the pressure remains constant at 900 kilopascal. So now at this point, so we know the volume at state 2, and we know that it is fully vapor, there is not a single drop of liquid. So it is fully the cylinder contained is saturated vapor. So and this is at 900 kilopascal. So at that point my specific volume is the specific volume of saturated vapor, which is we have already calculated, which is 0.0227 meter cube per kg, and my internal energy will be same as saturated vapor internal energy at 900 kilopascal. So that is 248.88 kilojoule per kg, and my corresponding enthalpies is 269.31 kilojoule per kg. So enthalpy we will require of saturated vapor, because that is the saturated vapor is what is escaping from the container. So at state 2, so we know volume, specific volume, we know the total volume of the cylinder. So now we can estimate what is the mass of the gas present when there is no liquid. So that is 1.57 kg. So the mass which has escaped out is nothing but the change in mass. So initially it was 16 kg, now we have 1.57 kg. So that gives me 14.43 kg. So that is the amount of saturated vapor which has escaped from the cylinder. So now if we apply a control volume across this gas cylinder and we apply a flow energy equation, what we get is, similarly or else can just straight away write it, rate of change of in my internal energy is equals energy coming in minus energy going out. So my dCV by dt is the rate of change of energy, and since we neglect kinetic energy and potential energy inside, we can straight away write this internal energy change equals my energy coming in is Q, heat which I am providing, and there is no inlet fluid which is coming in, so the inlet is 0. My exit is my saturated vapor which is leaving the cylinder, so minus m dot E He. So another equation is my mass flow equation. So similarly dmCV by dt is the mass leaving minus m dot E. So substituting m dot E from this mass balance equation and rearranging, this is what I get. So du Cv by dt equals q dot plus He dmCV by dt. So my exit enthalpy is nothing but my saturated vapor gas which is coming out. So He is Hg, and du Cv is, you can write it as mass into specific internal energy. so mu, so expanding it, integrating it over time. So what we get is m2 u2 minus m1 u1 equals q plus hg m2 minus m1. Q, there was rate of heat, now integrated you get the total heat. So substituting all the values here, we can find out q as 2515.28 kilojoule, so close to 2500 kilojoules. So what you are supplying to maintain it at 900 kilopascal. So next is when we apply an entropy balance for this process. So we get sigma dot is dSCV by dt plus m dot E SC plus q dot surrounding by T naught. So substituting these values here, so dSCV by dt is nothing but m dot into S. So integrating it, we will get m2 S2 minus m1 S1 minus Sg is the gas which is leaving, and dmCV by dt is m2 minus m1 plus q surrounding by T naught. So substituting the entropy values, similarly for at state 2 is your saturated vapor, and S1 we have to calculate for the two phase, and Sg is again saturated vapor entropy, and we know the masses, and we have q surrounding, we have calculated how much heat is being supplied. So for that, q surrounding will be negative of the heat which is being supplied. So for the system the heat is gained, but for the surrounding is losing heat. So the negative, there will be negative sign here, so should be careful there. And then T naught is your reservoir is at 50 degrees Celsius, so 273 plus 50. So substituting all this, we will get entropy generated as 361.54 joule per Kelvin. So next is we have a rigid well insulated tank is filled initially with 5 kg of air at a pressure of 5 bar and a temperature of 500 Kelvin. So a leak develops and air slowly escapes until the pressure of the air remaining in the tank is 1 bar. So employing the ideal gas model, determine the amount of mass remaining in the tank and its temperature. So if you see in the previous case, we know that we are maintaining that at 900 kilopascal, so there was no we were supplying heat to maintain that pressure. But in this case it is being insulated, so my inlet conditions will vary with time, so my gas which is leaving will also vary with respect to time. So so what is given is, we just like that, we have a cylinder or a tank which is having 5 kg of air at 5 bar and the temperature is at 500 Kelvin. So a leak develops and air slowly escapes, so there is slow leak until the pressure is 1 bar. So we need to find out how much mass is remaining in the tank and what is the temperature. So just like how we did it previously, we will do the same calculation here. So initial with the ideal gas equation, so the mass initially in the tank that remains in the tank at the end of the process. So I'll just repeat the question and I'll start. I just started this question. So we have a tank which is insulated and there is a small leak from the tank. So the initially the tank contained 5 kg of air and at 5 bar, and the temperature is at 500 Kelvin. So after the leak, so the gas is expanding and it's coming to a pressure of 1 bar. So at this point, how much gas is left in the tank and what is the temperature of the tank? So that's what is been asked. So uh, so here it's a control volume, so we have put across the tank. So and if you see the small box, we are assuming that is what is will be left after uh, the gas is expanded. So the mass which is present is P2V by R of the gas into T2, and similarly for mass at state 1 is P1V by RT. This is from the ideal gas equation. So M2 is P2 by P1 into T1 by T2 into M1. So this is the relation between the mass at state 2 and mass at state 1, because my volumes are same. So for this closed system under consideration, there are no significant irreversibility and no heat transfer which is occurring. So with that, the entropy balance will become 0. So since the system mass remains constant, so what we have shown here is this what indirectly they meant slow leak is what there is no irreversibility which is happening, and so delta S is equals to 0. So delta S equals to 0 is like an your adiabatic process, reversible adiabatic process. So that is the initial and final states of the system have the same value of specific entropy. So S2 minus S1 is Cp ln T2 by T1 minus R ln P2 by P1. So your temperature at state 2 will be, substituting these pressures and temperature 1, we will get temperature at state 2 as 317 Kelvin. So if you do this, what you will get is P2 by P1 is equals T2 by T1 raised to power gamma minus 1 by gamma. So that is equivalent to your reversible adiabatic process, expansion of reversible adiabatic process. So that's what you get. So you can use that also. So to find out T2, which is equals to 317 Kelvin. So finally, substituting these values, we will find out that mass which is present at the end of the process is 1.58 kgs. So moving on to next question. So air enters a turbine operating at steady state at 8 bar and 1400 Kelvin and expands to 0.8 bar. The turbine is well insulated and kinetic and potential energy effects can be neglected. So assuming ideal gas behavior for the air, what is the maximum theoretical work that could be developed by the turbine in kilojoule per kg for air flowing? So what we have is this turbine is working at a steady state, and your inlet is given and exit pressure is given, and this being well insulated, and assuming ideal gas behavior, we need to find out how much work can be produced. So applying a steady flow energy equation. So this is what the equation looks like. So your mass will all remain same. There is only one inlet and one outlet, and there is a steady flow. So there is no mass accumulation inside the system. So mass which is coming in will also go out. So m dot 1 is m dot 2 equals m dot, and then you are applying your first law. So dECV by dt equals q minus w plus mass into inlet stream minus exit stream. So enthalpy in minus enthalpy out plus your kinetic energy difference and potential energy differences, which we assume it negligible. So assume it to be 0. So since the turbine is insulated, there is no heat transfer, so Q is 0, and since it's steady flow, so there is no rate of change of internal energy, so dou EC by dou T is 0. So your work done is nothing but m dot into H1 minus H2. So to find the maximum value of H2, we use the entropy rate balance. So when we apply second law, so dou SCV by dou T is summation of Q by T, the heat transfer, plus m dot S1 minus S2 plus the rate of entropy generated. So there is no heat interaction, so that will be 0, and dou SCV by dou T is 0 because the steady flow equation. So your entropy generated should be greater than 0, so that implies that S2 minus S1 should be greater than 0. So S2 minus S1 should be greater than 0, so which implies that entropy should be increasing, so S2 should be greater than 1, S1. So we can only move to the right and not to the left. So initially you are at this point state 1, which is at 8 bar and 1400 Kelvin, and you have to come to 0.8 bar. So along this isobar in the TS plane, 0.8 isobar, when you are dropping straight down from 1 to 2 S, so vertical line, so that's the starting point where you can come to, and you can only go to right, and that's what the second law also says. So the greatest change in specific enthalpy, which corresponds to maximum work, is obtained when the expansion occurs in a internally reversible process. So the corresponding exit state is when S2S is equals S1. So your entropy at inlet is equals to entropy at the exit, which is equals to R ln P2 by P1. So S0 at TS is 2.70119 kilojoule per kg Kelvin. So substituting the values here and interpolating, we get a temperature as 788 Kelvin, or your enthalpy as 808.8 kilojoule per kg. So your work will become H1 minus H2S is 1515.42 minus 808 is 706.6 kilojoule per kg. So basically what just shown this, that's what even second law says, that if you entropy generated, the entropy generated is because of friction, and you expend some energy to overcome this friction, and then in that process you lose some of the work which has been developed in the turbine, and that's by making the internal entropy generated 0, that is by making the process internally reversible, S2 becomes equals to S1, and you follow an isentropic process. So you follow reversible isentropic, which gives you a maximum work done. So moving on to the next one. So next question is, air is contained in a rigid tank of volume 1000 liters. So the air is initially at 1 megapascal and 300 Kelvin. So a valve on the top of the tank is now opened, and the air is allowed to escape slowly into the atmosphere until the pressure of the vessel reaches 100 kilopascal, at which point the valve is closed. So temperature of air inside the tank is maintained constant as a result of heat transfer with the ambient at 27 degrees Celsius. determine the mass of air that escapes, the heat transfer and the entropy generated during the process. So this is similar to the previous one, but this is like a combined problem of what we saw the first two, R134 AKs and then air. So here also they are not letting the temperature to vary at 27 degrees Celsius. So we'll see how to solve this. So what we know initially is volume is 1000 liters and your pressure is 1 megapascal and temperature is 300 Kelvin. At state 2, when the air has escaped, your pressure is 100 kilopascal. So now we need to calculate how much mass of air has escaped. So we can calculate m1 minus m2 is your volume into p1 minus p2 by RT, because your temperature is constant and volume is constant. So this becomes 10.45 kgs. So that is the amount of mass of air which has escaped. So next is applying an energy balance equation for the tank. We get dE CV by dt, which is dou U CV by dt, which is q dot minus m dot exit into He, and similarly mass balance. So when we combine this, we get dou U CV by dou T equals q dot plus He into a dm CV by dt. So when we integrate this, what we get is m2 u2 minus m1 u1 equals q plus Cpt is the enthalpy of air at exit into m2 minus m1. So rearranging it, we can find out q, and your individual masses can be found out using ideal gas equation as PV by RT. So substituting those and the temperatures, we get the heat which is supplied is 900 kilojoules. So next is we need to find out how much entropy has been generated in the process. So for this, the rate at which the entropy is generated for a flow process is given by sigma naught is dSCV by dt plus m dot exit stream entropy minus inlet stream entropy plus q surrounding by T naught. So since there is no inlet, so there is only gas escaping, so m dot I is 0. So q surrounding is nothing but my q which is heat interaction gained by the system. It's opposite of what surrounding. My system is gaining heat, then surrounding is losing heat. So substituting the values here. So dS is your total entropy. We are writing in terms of specific entropies here, and then it gets simplified to entropy generated as mCV dSCV by dt plus q surrounding by T naught. Since my entropy change is temperature change is 0, as I am maintaining at same constant temperature, so dSCV is minus R dP by P. So integrating that, I'll get minus R ln P2 by P1. So substituting dSCV by dt as minus R dP by P, I get minus V by T P2 by P2 minus P1 plus minus Q system by T naught, which will come out to be 0 kilojoule per Kelvin. So moving on to next question. moving on to next question. A rigid vessel of volume 600 liters contains 8 kg of water at 20 bar. So liquid is now allowed to escape slowly from the bottom of the vessel. So heat is transferred from a reservoir at 250 degrees Celsius to the vessel so as to maintain the pressure constant. So the process is stopped when no more liquid remains in the vessel. Find the mass that escapes, heat transferred, and entropy generated. So we know the vessel volume, which is 600 liters, and the initial mass is 8 kg of water, which is at 20 bar. So we are letting the water escape from the bottom, and heat is transferred from the reservoir at 250 degrees Celsius to the vessel so as to maintain the pressure constant. So at initial state, so the specific volume is evaluated at, so V1 is V by mass 1 mass at the initial state. So volume is 600 liters, this 0.6 meter cube divided by your initial mass, which is 8 kgs. So that gives you the specific volume of 0.075 meter cube per kg. So at 20 bar, my specific volume of liquid is 1.177 into 10 power minus 3 meter cube per kg, and for saturated steam is 0.1 meter cube per kg. So we see the volume lies between these two, so it should be a two-phase mixture of both. So we need to find out what is the dryness fraction or the mass, the fraction of vapor which is being present. So x1 is V1 minus Vf divided by Vg minus Vf. So this gives you 0.747. So that means 74 or close to 75% is vapor. So at the final state, saturated vapor fills the entire vessel. So what they have said, the process stops when no more liquid remains in the vessel. So the whole vessel contains vapor, and we are supplying heat to maintain it at constant pressure. So we know the specific volume at gas, which is 0.1 meter cube per kg. So your mass at state 2 is, we know the total volume, so volume divided by the specific volume of saturated steam gives you 6 kgs. So the mass of vapor is 6 kgs. So mass of vapor that has escaped is m2 minus m1 is 2 kg. So from energy balance we can find out, and mass balance we will get the equation like this. So du Cv by dt equals q dot into He dm Cv by dt. So this is just combined equation of your energy balance and mass balance. So here there is only one exit stream and there is no inlet stream, and your work done is also 0. So q dot plus He is your saturated liquid here, which is exiting. So He into dm Cv by dt. So dmu Cv by dt equals q dot plus Hf dm Cv by dt. So m2 u2 minus m1 u1 equals q plus Hf m2 minus m1. So after integrating, this is what we get. So Hf is 908.8 kilojoule per kg, and Ug is 2600 kilojoule per kg, and Uf is 906.4 kilojoule per kg. So using this we can find out initially the internal energy present. So it comes out to be Uf plus x1 is a dryness fraction into your saturated vapor or saturated steam internal energy minus your saturated liquid internal energy, which comes out to be 217.1.52 kilojoule per kg. So substituting this in the above equation, your heat supplied is 45.44 kilojoules. So now we need to do entropy balance to find out how much entropy is generated in the process. So to do that, we need to find out the entropies at each of the states. So at state 1, we know this is in two phase, so we need to find out saturated liquid and saturated vapor entropies, and then for the mixture, so S1 is SF plus X1 into Sg minus SF. So S1 is 2.447 and sorry, SF is 2.447 and a saturated steam entropy 6.341, and we know Reynolds fraction is 0.747. Substituting, we will get entropy at state 1 is 5.356 kilojoule per kg, and entropy at similarly at state 2. So state 2 is fully saturated vapor or saturated steam. So at same pressure, so my entropy is same as saturated steam, which is 6.341 kilojoule per kg. So the rate of entropy generated is given by sigma dot is dSCV by dt minus SF dmCV by dt plus Q surrounding by T naught. So sigma is M2 S2 minus M1 S1 minus SF M2 minus M1 plus Q by T naught. So substituting the values here, so here exit enthalpy is your saturated liquid enthalpy. So SF is saturated liquid, which is 2.447, and the final and initial mass is also known. So substituting, we get 6 into 6.341 minus M1 is initially 8 kgs into entropy at state 1, which is 5.356, minus the enthalpy of entropy of stream which is leaving this saturated liquid which is 2.447 into change the mass which has escaped, which is 2 kgs, minus heat supplied 45.44 divided by 273 plus 250. That is my reservoir temperature. So that gives me the entropy generated as 5.116 joule per Kelvin. Next is helium gas is throttled steadily from 400 kilopascal and 60 degrees Celsius. So heat is lost from the helium in the amount of 1.75 kilojoule per kg to the surroundings at 25 degrees Celsius and 100 kilopascal. So the entropy of the helium increases by 0.34 kilojoule per kg Kelvin in the valve. Determine A, exit pressure and temperature, and B, the entropy generation during the process. So what is given is, we have helium gas which is throttled steadily, so it's a steady process and it's being done. The inlet is at 400 kilopascal, which is 4 bar, and 60 degrees Celsius. So heat is lost from the helium in the amount of 1.75 kilojoule per kg. So that is the amount of heat which is lost to the surrounding. And the surrounding is at temperature of 25 degrees Celsius and 1 bar. So during this throttling process, they are saying that if the entropy of the helium increases by 0.34 kilojoule per kg Kelvin in the valve, we need to determine what is the exit pressure and temperature and how much entropy is generated. So for helium, Your gas constant is 2.0769 kilopascal by kg Kelvin. So Cp is 5.1926 kilojoule per kg Kelvin. So what we need to find out first is we need to find out the final temperature, and what we do is we'll apply an energy balance across this valve. So there is a helium which is coming in at 400 kilopascal and 60 degrees Celsius and is passing through the valve, and there is a heat transfer to the surrounding. So when we apply an energy by steady flow energy equation, so energy coming in equals energy going out, because there is nothing accumulated in the system. So energy which is coming in will go out. So energy coming in is m dot into h1, then equals q plus m dot into h2. So q is nothing but m dot h1 minus h2. So enthalpy can be written as Cp into T. So here q is Cp into T1 minus T2. So here we can find out temperature at exit. So T2 as T1 minus Q out by Cp. So we know the inlet temperature is 60 degrees Celsius and the heat transfer is 1.75 kilojoule per kg divided by my Cp, which is 5.1926, so which gives me 59.7 degrees Celsius. So we know the final temperature at the exit. We need to find out the final pressure may be determined using the change in entropy. So delta S of helium is Cp ln T2 by T1 minus R ln P2 by P1. So here they have been given the entropy rise in helium is for the process 0.34 kilojoule per kg Kelvin. So delta S is given. So for this process the entropy change is Cp ln T2 by T1 minus R ln P2 by P1. So equating that, so change in entropy is 0.34. So Cp value is given 5.1926 into ln of T2, which is 59.7 or 332.7 Kelvin divided by 333 Kelvin minus R, which is 2.0769 ln P2 by P1. P1 is 400 kilopascal. So solving this, we get pressure P2 as 339 kilopascal. So now we need to find out the entropy generated. So entropy generated is nothing but your entropy of system plus surrounding. So entropy of system we know, which is 0.34, plus surrounding is Q out by T surrounding. So heat transfer is 1.75 kilojoule, which is gained by surrounding, divided by T surrounding is it's at 25 degrees Celsius, so 273 plus 25. So this comes out to be 0.346 kilojoule per kg Kelvin. So that is the amount of entropy which is being generated. on to next question. An adiabatic air compressor is to be powered by a direct coupled adiabatic steam turbine that is also driving a generator. So steam is entering the turbine at 12.5 megapascal and 500 degrees Celsius at a rate of 25 kilograms per second and exits at 10 kilopascal and a quality of 0.92. So air enters the compressor at 98 kilopascal and 295 Kelvin at a rate of 10 kg per second and exits at 1 megapascal and 620 Kelvin. So determine the net power delivered to the generator by the turbine and the rate of entropy generation within the turbine and the compressor during the process. So both inlet and exit conditions are specified for both the compressor and the turbine. So what they have said is both are adiabatic, so there is no heat interaction, and this turbine is coupled with the compressor and the generator. So whatever the power is generated by the turbine, so part of it is getting utilized in running the compressor, and the remaining is what is sent to the generator, and you are getting it as work or electricity. So for both the compressor and the turbine, the inlet and exit conditions are specified. The two parameters are given to locate the state point. So two properties are known. So with that, we'll see how to solve this. So T1 is at 295 Kelvin and 98 kilopascal. Correspondingly, for air the enthalpy is 295.17 kilojoule per kg and entropy is 1.68515 kilojoule per kg Kelvin. And for temperature at state 2 at 620 Kelvin, the enthalpy is 628.07 kilojoule per kg and the entropy is 2.44356 kilojoule per kg Kelvin. And the property is also given to make it easier. So P3 is 12.5 megapascal and T3 is 500 degrees Celsius. So from steam table you can find out enthalpy at your turbine inlet is 3343.6 kilojoule per kg and the entropy is 6.4651 kilojoule per kg Kelvin. And the exit of the turbine is known to be at 10 kilopascal and my dryness fraction is 0.92. So enthalpy at state 4 is a two phase. So H4 is HF plus X into HFG. So substituting the values, we will find out at 10 kilopascal. So my enthalpy at state point 4 is 2392.5 kilojoule per kg and entropy is 7.5489 kilojoule per kg Kelvin. So applying an energy equation, so my energy in is energy out is the energy rate of change of my system energy. So since it is a steady equation, so energy in is equals to energy out. So for the turbine and compressor, so compressor in work plus m dot of air H1 equals m dot of air H2. So compressor in is m dot of air H2 minus H1, and similarly for turbine, m dot of steam which is coming at H3 is the inlet equals the turbine out plus m dot steam H4. So the turbine work is m dot steam into H3 minus H4. So substituting the values here, so compressor work which is in, so so should be in a negative sign, so we have put it in, means it's coming into the system which is negative. So 10 into 628.07 minus 295.17 gives you 3329 kilowatt. So that is the amount of work which is has to be provided to the compressor, then the turbine, which is 25 into your enthalpy change, so that is 23777 kilowatt. So the net out of this coupled compressor and turbine is your turbine output minus compressor in, which gives you to 20,448 kilowatt. So that is the net work which is sent to the generator. So you see the system is adiabatic, so the total rate of entropy change during the process is just the entropy change because of the stream inlet and coming in and going out. So Sgen is m dot of air S2 minus S1 plus m dot steam S4 minus S1. So m dot of air is S2 minus S1 is 0.92 kilowatt per Kelvin, and the entropy of the steam change is m dot steam into S4 minus S3 is 27.1 kilowatt Kelvin. So adding both up, you get 0.92 plus 27.1, which is 28.02 kilowatt per Kelvin. So that is the total entropy generated for the compressor and the turbine. So two rigid just a So the two rigid tanks are connected by a valve. Tank A is insulated and contains 0.3 meter cube of steam at 400 kilopascal and 60% quality. Tank B is uninsulated and contains 2 kg of steam at 200 kilopascal and 250 degrees Celsius. So the valve is now opened and steam flows from tank A to tank B until the pressure in tank A drops to 200 kilopascal. During this process, 300 kJ of heat is transferred from tank B to the surrounding at 17 degrees Celsius. Assuming the steam remaining inside tank A to have undergone a reversible adiabatic process, determine A, the final temperature in each tank, and B, the entropy generated during this process. So what we have here is, we have two tanks which is connected by a valve, and the tank A is insulated and tank B is not insulated. So there is insulated tank which is connected by a valve to another tank, and tank A is of 0.3 meter cube and is containing 400 kilopascal of steam, and my vapor fraction is 0.6. And in tank B initially contains 2 kg of steam at 200 kilopascal and 250 degrees Celsius. So one is given in terms of volume and other is given in terms of mass. So we can find out either. So first case we know the vapor fraction and the pressure with which we can estimate the specific volume, and since we know the volume we can find out the mass. So tank A quantities can be measured, found out, and tank B is they are given mass. So similarly we know the pressure and temperature, we can estimate specific volume and then estimate the volume. So the valve is now opened and steam flows from tank A to tank B until the pressure in tank A drops to 200 kilopascal. So during this process, 300 kilojoule of heat is transferred from tank B to surrounding at 17 degrees Celsius. So now after the valve is open, steam starts flowing from tank A to tank B, and tank A pressure drops to 200 kilopascal. So all comes into equilibrium at 200 kilopascal. During this process, 300 kilojoule of heat is transferred from tank B to surrounding at 17 degrees Celsius. So, and they are saying that tank A goes through a reversible adiabatic process, which we have already seen in the previous problems, that the expansion is happening is a reversible adiabatic process. So here they have explicitly mentioned that. So what we have been asked to find out is the final temperature in each of the tanks and the entropy generated during this process. So this is how the system looks. So initially there is a tank which is insulated, it's at 0.3 meter cube and 400 kilopascal, and Reynolds fraction is 0.6, and which is connected by a valve to another tank which is not insulated, and that is rejecting 300 kilojoules of heat to the surrounding, which is at 17 degrees Celsius, and their initial mass is 2 kg and temperature is 250 degrees Celsius and pressure is 200 kilopascal. So for this we need to find, let's estimate what is the initial conditions. So for tank A, my pressure initial is 400 kilopascal and Reynolds fraction is 0.6. So my specific volume is Vf plus x into Vfg, which comes out to be 0.27788 meter cube per kg, and internal energy at state 1 for tank A is similarly Uf plus x Ufg, which comes out to be 1773.6 kilojoule per kg, and entropy for tank 1 at state 1, tank A at state 1 is again Sf plus x into Sfg. So entropy for tank A at state 1 is 4.8479 kilojoule per kg Kelvin. So the initial temperature at this point is the saturated temperature corresponding to 400 kilopascal, which is 120.2 degrees Celsius. Then my tank A pressure drops to 200 kilopascal when the valve is open. So at this point, this tank A has gone through an reversible adiabatic process, so my entropy remains same. So my initial entropy and final entropy are same. So I know the state 2 of tank A. So tank A state 2 is pressure is 200 kilopascal and the entropy is same as the initial entropy. So using this, T2A is Tsat at 200 kilopascal, which is 120.2 degrees Celsius. Sorry, this is a temperature at 2, which is 120.2 degrees Celsius. Then X2A is the dryness fraction, is S2A minus SF by SFG. So I know my entropy and I know the corresponding saturated and vapor, liquid and vapor entropies for 200 kilopascal. So substituting this, I can estimate the dryness fraction comes out to be 0.5928, and similarly specific volume at state 2 is 0.52552 meter cube per kg, and my internal energy is 1704.7 kilojoule per kg. So this is my initial and final states for the tank A. So similarly for tank B, initially it is at 200 kilopascal and 250 degrees Celsius. So corresponding values are, specific volume is 1.1989 meter cube per kg, and my internal energy is 2731.4 kilojoule per kg, and entropy 7.71 kilojoule per kg Kelvin. So with this I can find out the initial masses. So initial mass in tank 1 is V by specific volume, which is 0.3 by specific volume at state 1, which is 1 point, it will come out to be 1.08 kg at state 1 for tank A. Similarly at state 2, after the valve is open, my specific volume is known, I have calculated. So mass at state 2 is, again the volume is constant, so 0.3 by specific volume at state 2, which is 0.5252552. So mass is 0.570, so close to half a kg has escaped. So the mass which has escaped is 1.080 minus 0.5709, which comes out to be 0.5091 kg of mass which is flown from tank A to tank B. Then M2B is the mass at tank 2 at state 2, is the mass initially present and the mass which has entered from tank A to tank B, which is we have calculated 0.5091. So initially it had 2 kgs and additionally half a kg has come. So the state 2 total mass for tank B is 2.5091 kgs. So with this, the final specific volume of steam in tank B can be determined. So M1V1 is the volume of tank B divided by mass of state 2. So 2 into 1.1989 divided by 2.509 gives me 0.9558 meter cube per kg. So that is the specific volume at state 2 for tank B. So now for the tank B, we won't know only one property, which is the specific volume. So we need to find out the rest. So we will apply an energy balance. So Q out is delta U, change in internal energy. So since there is only heat interaction, there is no work interaction, and there is no mass coming in and going out, so minus Q out is your delta U. So delta U is delta UA plus delta UB. So minus Q out is M2 U2 minus M1 U1 plus M2 U2 minus M1 U1 of B, tank B. Substituting all the values, so only unknown is the internal energy at state 2, so which comes out to be 2433.3 kilojoule per kg. We have found out the internal energy, which is 2433.3 kilojoule per kg, and the specific volume, which is 0.9558 meter cube per kg for tank B at state 2. So with this both state points we need to find out by doing an iteration in the steam table. State 2B, which comes out to be 116.1 degrees Celsius. Next to entropy corresponding to that state is 6.9156 kilojoule per kg Kelvin. Since temperature is unknown, we need to do an entropy generator. So total entropy generation during this process is determined. We do an entropy balance for both tank and the immediate surrounding. So S in minus S out plus entropy generated is the entropy change in the system. So minus Q out by T surrounding plus S generated equals delta SA plus delta SB. So S gen is delta SA plus delta SB plus Q out by T surrounding. So substituting the values here, so since at A both it goes through a reversible adiabatic process which is specified, so entropy change will be 0, so that as change entropy change in tank A will be 0, so you can straight away write this is 0, and so it will come out to be M2S2 minus M1S1 for tank B plus Q out by T surrounding. So substituting the entropies and mass of tank B and Q is given as 700 kilojoule and at 17 degrees Celsius, so 290 Kelvin. So this comes out to be 0.498 kilojoule per Kelvin. So that is the total entropy generated. So next and final question which I have prepared for today. So we have a refrigerant R134A which is compressed from 2 bar saturated vapor to 10 bar at to 90 degrees Celsius in a compressor operating at steady state. So the mass flow rate of refrigerant entering the compressor is 7 kg per minute and the power input is 10.85 kilowatt. So kinetic and potential energy can be neglected. So determine the rate of heat transfer in kilowatt. Next is, if the heat transfer occurs at an average surface temperature of 50 degrees Celsius, determine the rate of energy production. Determine the rate of energy production, entropy production of for an enlarged control volume that includes the compressor and its immediate surrounding, such that a heat transfer occurs at 300 Kelvin. So what it says, difference between B and C is you're doing the heat transfer, so your reservoir temperature is 50 degrees Celsius and here it is 27 degrees Celsius, so that's the difference. So your inlet is at 2 bar and saturated vapor and 7 kg per minute, and it's coming out at 10 bar and 90 degrees Celsius, and your boundary temperature is 50 degrees Celsius and Q. So initially you are applying just to that boundary, so your boundary is at 50 degrees Celsius. Now you are taking in some of the surrounding to So that reservoir temperature is now at 27 degrees Celsius. So that's the difference between the B part and C part. So applying an energy balance across this compressor, so Q minus W plus M H1 minus H2 plus your kinetic energy and potential energy terms, which can be neglected. So Q minus W plus M H1 minus H2. So solving, we'll get Q as W plus M H2 minus H1. So that is the amount of heat which is taken in. So at state 1, which is a 2 bar and saturated vapor, so enthalpy corresponding to that point is 241.3 kilojoule per kg, and entropy is 0.9253 kilojoule per kg Kelvin, and state 2 is the 10 bar and 90 degrees Celsius, which is a superheated vapor. So corresponding to this pressure and temperature, my enthalpy is 324.01 kilojoule per kg, and entropy is 1.0707 kilojoule per kg Kelvin. So substituting that, Q is given that it consumes 10.85 kilowatt, so minus 10.85 because we are giving in, so minus 10.85 plus 7 into your enthalpy change, so that comes out to be minus 1.2 kilowatt, minus 1.2, so that says heat is rejected. So now applying the steady state entropy balance for the system. So dCV by dt is 0, so QCV by your boundary temperature plus m dot S1 minus S2 plus sigma entropy generated. So entropy generated is minus 1.2 kilowatt by 323 plus a mass into entropy change. So that comes out to be 0.02068 kilowatt per Kelvin. So now since we are taking into account the surrounding enlarged volume, so your surrounding temperature at is at 300 Kelvin instead of 323. So in that case, entropy generated is 0.02096 kilowatt per Kelvin. So the entropy generated is because of the fluid. This has been already discussed in the previous week, that this happens because of fluid friction and so on in the compressor, and friction in the bearings and so on, and there is an internal heat transfer which is also happening, which also increases your entropy chain generation. So it is already seen that having a temperature difference causes entropy production, so that is what is driving entropy generation here. So this is just for the system, and the total entropy production we have to calculate for the surrounding as well. And with that, I have finished what I prepared for today. with that I have finished what I prepared for today. Since there is no other queries, so I'll close the session for today. I'll be uploading the video and the slides, and the link will be, can be seen by you. So next week we will see the exergy balance and exergy, how to estimate exergy and do an exergy balance and so on. So this entropy generated and all will be better understood when exergy comes to play, because entropy is very difficult to imagine, but that has a consequence, and as a mechanical engineers we can always deal with work. So how that is entropy generated is gives you a relation to exergy, will be seen in the next weeks, and we will also see some numericals on those. So thank you. See you next week.